Hi everyone. In this video, we will look at some consequences and extensions of the definition of the Lebesgue integral of a bounded function. Primarily, this video will be broken into two components. The first in which we examine criteria for Riemann integrability from both Riemann's and Lebesgue's perspectives, and then an extension of our definition of the Lebesgue integral of a bounded function to a definition of a Lebesgue integral of an unbounded function. So I want to begin with a definition, and this definition will be important because it will allow us to express in a particular way Riemann's criteria for Riemann integrability of a function. So let f be a bounded real-valued function. Then we can define the oscillation of the function f both on an interval and at a point. So we define the oscillation of a function f on the interval I as omega of fi. So omega is the oscillation, and that is a function of a function f and an interval I. That is defined to be the supremum over all s and t in the interval I of the absolute value of f of s minus f of t. So one way to think about this oscillation, I have some function, I have some interval, okay, and f of s minus f of t in absolute values, that's just the difference between two different outputs of the function, right? But what I'm looking for is I'm looking for the supremum of that difference over the entire interval. So on this particular interval, maybe I would take, it looks like the lowest value of the function is here. The supremum of this difference is going to occur at this endpoint here, even though maybe it's not necessarily included in the interval. That's why we look at a supremum of this difference. And so the oscillation of the function would just be this difference here, okay? So it's called the oscillation of the function because on an interval, it's measuring how much the function oscillates, sort of the difference between the lowest and the highest points in a way. Even though, as in this case, it's not exactly the difference between the lowest and the highest points because there is no highest point on this open interval I, right? If it was closed, then it would actually be achieved. So that's what the oscillation on an interval is measuring. The oscillation at a point essentially just says, okay, well, we can measure the oscillation on an interval, but if I want to measure the oscillation at a point, then what I do, so let's say I wanted to measure the oscillation at this point x, what I do is I take neighborhoods of this point x. On any neighborhood, I can calculate the oscillation. So the oscillation on, say, this neighborhood would be the same as the oscillation on this interval before. But then I start shrinking this down. And I look at the oscillation over every neighborhood containing x. And then I say, well, what's the infimum of all of those values, right? So I can define this oscillation quantity both at on an interval and at a point. It turns out what we really want here, right, is actually the oscillation on an interval, okay? And the reason we want this is going to help us express how Riemann, in a way, thought about what it meant to be Riemann integrable. So this theorem is what we'll call Riemann's criterion for Riemann integrability. So let f be bounded on the interval ab, then f is Riemann integrable on AB, if and only if. All right, for every epsilon and sigma greater than 0, there is a delta such that for any partition P with the norm of the partition P less than delta, it follows that if I add up the lengths of all the subintervals such that on that subinterval, the oscillation of the function is greater than sigma, and if that sum is less than epsilon, then it follows that f is Riemann integrable. So again, this is an if and only if. Okay. So let's think through this criterion a little bit. Again, it says this should work for any epsilon and for any sigma. Now, you really want to think of both of these as being relatively small. right? So really this gets challenging when sigma and epsilon are small. So I have some function f, I have an interval AB, okay, and then I fix a sigma and a epsilon. Okay, they're given to me. Now I want to show that I can choose a delta such that anytime I take a partition less than that delta, so I want to show that I can choose this partition fine enough, right? So that if I go through, and the first thing I'm going to do is I'm going to go through and I'm going to look at all of these partitions. And for the sigma you gave me, I'm going to ask myself, okay, on this first little subinterval, is the oscillation of the function greater than sigma? So maybe here it's not, so I'm not going to select that one. On the second one, maybe it's not. On the third one, maybe it's not. Maybe none of these has oscillation greater than sigma, but maybe, let's see, once my function starts to get a little steep over here, maybe this subinterval has oscillation greater than sigma. And maybe this subinterval does. And then maybe it doesn't for a while, and then maybe these two do. Okay. So then what I do is I take a sum, and again, I'm taking the sum just over the just of the lengths of the intervals where my oscillation is greater than sigma. So that's what this sum over all j such that the oscillation over ij is greater than sigma of delta xj. So I basically add together the lengths of these, and I want to show that that's good. Because of the way I chose my delta, this is going to be less than epsilon. Okay. So the idea here, essentially, like one way to say this, or another way to say this, is that f is Riemann integrable if and only if the sum of the lengths of the intervals where f varies by more than sigma is less than epsilon whenever the partition is small enough. Okay. So the idea here is I can always choose a partition small enough so that the sums of the lengths of these points where my function is oscillating more than sigma is very small, is as small as I'd like it to be. Okay. Now, when you sort of look at this criteria, I think it feels pretty unwieldy. I mean, you have sort of three different quantified variables, right? You have this epsilon, you have this sigma, you have this delta. So it's sort of a logically complex statement. And it's just also not immediately clear like how I would really use this. Okay. Now, the proof of this theorem essentially just follows from the formal definition of Riemann integrability. So you could prove this, you could prove this, but it's basically just sort of a technical proof using the definition of Riemann integrability. The funny, sorry, I was just thinking the book also talks about here, this is sort of the formal statement or I guess a formal summary of what this definition is saying. The book also provides this sort of rather humorous one, which says f is Riemann integrable if and only if it misbehaves in only a, if and only if f misbehaves in only a small collection of tiny neighborhoods, right? So this oscillation they're thinking of as sort of a measure of misbehavement, right? You're oscillating too much, so your function's misbehaving. But this says that your function only misbehaves in a small number of tiny neighborhoods. Now, Riemann certainly was sort of aware of this idea. Lebesgue was aware of this idea. And Lebesgue's insight into Riemann's sort of criteria here was that what this is really saying is that the function, it needs to be almost continuous, or at least the places where sort of it's not continuous, right? Because having large oscillation, right, would almost be one way to think of like having large oscillation at a point, or indeed non-zero oscillation at a point, would be to say that your function has a jump, right? So what he sort of, or some sort of discontinuity. So what what Lebesgue sort of realized was that, in a way, what this was saying is that the measure of the set of points of discontinuity needed to be arbitrarily small. Indeed, it needed to be zero. So, and that's exactly what Lebesgue's criteria for Riemann integrability is. So it essentially says let f be bounded on AB, then f is Riemann integrable if and only if f is continuous almost everywhere on the interval. Okay, so remember, right, what does this continuous almost everywhere mean? Right, it means that the measure of the set of x in AB such that f is not continuous at x, the measure of this set ought to be zero. Okay. Now, again, you sort of compare that to Riemann's criteria. It's really, in a lot of ways, saying the same thing. Riemann's criteria is saying, well, I can cover all of the points where the oscillation is greater than sigma, right? Really, if it was going to be continuous at a point, that oscillation should be getting arbitrarily small. I can cover all the points where the oscillation of the function is greater than sigma by a few small neighborhoods so that they don't add up to any more than length epsilon, right? And I can do that for any epsilon. So it really is saying that the measure ought to be, of the set, ought to be zero. Now, we're not going to formally prove this. There is a proof of this in the book. It's just sort of a technical proof. But what I want you to see is why this result is so powerful, particularly in just helping us understand like what the integrals of things ought to be. So I actually want to go back and examine a function that we really haven't looked at in this course, but we looked at in Math 5610. So that's Thomae's function. So recall that Thomae's function is defined on the closed interval 0, 1. And it's defined to be the function so that t of x, if x is rational, then you take x, since it's rational, you can express it as an integer p over an integer q. And let's assume that that's expressed in lowest terms. So if x is equal to p over q, then t of x returns 1 over q. But if x is irrational, then it just returns 0. So, for example, t of 6/8. Well, 6/8 is not in lowest terms, right? That should be 3/4, and then it just returns the denominator, so it just returns 1/4. T of 3/5 would be 1/5. T of pi over 10, well, that's irrational, so it would be 0. Okay. So one of the things we showed in Math 5610, right? We showed that the limit as x approaches a of t of x was equal to 0 for all a in 0, 1. Okay. Now, a consequence of this, right, is essentially that t is continuous at every irrational x, and it's not continuous, it's discontinuous at every rational x in 0, 1. Now, let's say we ask the question, is t Riemann integrable? Okay. And when you start asking questions about integrability, a first good question to ask is always, is it Riemann integrable? Because if it's Riemann integrable, then it's definitely Lebesgue integrable, right? We've already looked at that. Okay, so if t is Riemann integrable, then it is Lebesgue integrable. So let's ask, is it Riemann integrable? Well, we can use Lebesgue's criteria, okay? Because it's an if and only if, it's necessary and sufficient, right? So if we answer in the affirmative that the measure of the points of discontinuity is 0, if we answer in the affirmative let's phrase it this way. If we answer in the affirmative that the function is continuous almost everywhere, then it has to be Riemann integrable. If we answer in the negative that f is not continuous almost everywhere, then it's not Riemann integrable. Okay, so we can ask, is T Riemann integrable? Well, we need to look at the measure of the set of all x such that f is not continuous at x. Okay. Well, we know in this particular example, it's continuous at every x in this set, so it's only discontinuous on q intersect 0, 1. Okay. Well, this is a countable set. The measure of any countable set is 0. Okay. And so, by Lebesgue's criterion, okay, t is Riemann integrable. I'm sorry, this should be set of all x, where our function here is t, so that t is not continuous at x. So t is Riemann integrable. All right, and that automatically implies that it's also Lebesgue integrable. All right, well, that's great. So now the next natural question to ask, well, if it's Riemann integrable, what is its Riemann integral? Okay, can we compute the integral of this function? Now, again, I've often said, right, Calc 2 is all about calculating Riemann integrals, right? That's most of the content of a Calc 2 course. There's some sequences and series stuff, but mostly it's about calculating Riemann integrals. But none of those things work here, right? This is not, they're really all strategies for integrating sort of sums, products, quotients, differences, compositions of elementary functions. And this is in no way composed in that fashion, right? So I want to compute. So the next question, right, separate from, is it Riemann integrable? The answer to that certainly is yes. We can answer that sort of theoretically. Now, the practical question is, can I compute the Riemann integral of t of x? Okay. Well, excuse me. The integral from 0 to 1 of t of x, the Riemann integral, well, it actually has to be equal to the Lebesgue integral. Now, this seems counterintuitive, right? It seems counterintuitive to compute a Riemann integral by a Lebesgue integral because we actually feel like we don't have any tools really for calculating those things. Okay. Well, we maybe don't have a lot of sort of tools, but we do have a lot of theory. So what I want to note is that this is equal to the integral, the Lebesgue integral of 0 d mu. Now, why is that true? Well, t of x is equal to 0 for all irrational x in 0, 1. And t of x is not equal to 0 for all rational x in 0, 1. Well, what does this mean? This really means that t of x is equal to 0 almost everywhere in 0, 1. So said another way, t of x is equal to 0 almost everywhere in 0, 1, because the only place it's not equal to 0 is on this set, but this set has measure 0. Well, one of the properties of Lebesgue integration is that if f is equal to g almost everywhere, then the Lebesgue integral of f is equal to the Lebesgue integral of g. Okay. Well, now what is this? This is it's a constant function. It's a simple function though, right? And how do I integrate simple functions? Well, the only value here is 0 times the measure of the set where it's 0. Well, it's 0 on all of 0, 1. Okay. And so this is just 0 times 1, which is 0. So here, we're actually able to compute that the Riemann integral of this function is 0, but we do it by using properties of the Lebesgue integral and using the fact that since it's Riemann integrable, it must have a Lebesgue integral. So this is a really nice, I really like sort of concluding some of this stuff about integrating bounded functions with this example, because it really shows the power of all this theory to help us compute values of not only Lebesgue integrals, but also Riemann integrals. All right. Now, in addition to, being able to use this theory, to help us compute integrals, we can also expand this theory to deal with the Lebesgue integral of an unbounded function. So far, we've been dealing with the Lebesgue integrals of bounded functions. We think about the whole sequence, we started with the Lebesgue integral of a simple function. We were able to use that and come up with a definition for the Lebesgue integral of a bounded function. And now we're going to extend that definition to help us deal with the Lebesgue integrals of unbounded functions. Now, before we can just jump straight into that, we need an additional definition. And so we want to define the n truncation of a function. So let f be a non-negative function on the interval ab. Then the n truncation of f is just the function f sub n of x is equal to the minimum of f of x and n. Okay. Now, before we continue to the rest of this, let's just think sort of what's happening here. Now, we can take the n truncation of any function, but in particular, we're thinking about applying this to unbounded functions. So let's take an interval ab, and imagine you have a function that is unbounded on this interval. So you can sort of imagine something like this. Now, it's important when we start here to remember that in Lebesgue integration, we allow functions to be extended real valued. So I would say that this function f is defined on this entire interval ab. It just happens to be that f of c is equal to infinity. So while this function is not bounded, it is defined on the entire interval ab if I can think of it as an extended real value function. Now, this is different than Riemann integration, right, where I just think about real valued functions, and this function would not be defined on the entire interval ab. So in Riemann integration, you have to deal with the fact that c is not in your domain. Okay, and so that's why, right, if you were dealing with this in Riemann integration, you would sort of cut here, and then you would look at what happens, say, as this point x1 goes to c from below. Maybe this is x2, let that go to, like, you have to do some sort of limiting in the domain. That's not necessary, however, for Lebesgue integration, because we actually think of this function c as being, or sorry, this function f as being defined here at this point c. Okay, it's just that the value happens to be infinity. Now, these truncations, okay, so you can imagine here in your domain, so let's say you have, like, here's 1, here's 2, maybe I'll extend this up a little bit more, here's 3. So the one truncation basically says, well, you come here at 1, so like there's the height 1, and if the value of the function is below 1, you keep the value of the function. If it's above 1, you just make it 1. Okay. So in red here is the n truncation f1, or the one truncation f1. The two truncation, all right, you come across at 2. Okay, if your function is above 2, you just bring it down to 2. If it's below 2, you keep the function value. All right, so in blue here we have the 2 truncation f2. Okay, now you're probably beginning to see sort of what's going on here. So just one more, right? The 3 truncation. Okay, anything above 3 gets rounded down to 3. Everything below 3 I keep. And this gives me my function f3. Okay, and I can do this for any n. Okay, now a couple of things to note. The sequence of f sub n's, they converge monotonically to f on the closed interval ab. Okay, so What does that mean? It means I'm converging to f, right? And this sequence, like if you fix an x, so say you fix some value x star in AB, then this is going to be a non-decreasing sequence, okay? So this is non-decreasing, so monotone. So it's like imagine you picked, say, x star right here. So f1 of x star would be 1. f2 of x star, say, would be 2. Then f3 of x star maybe would be whatever f of x star was. And then that would be the same as n kept going, right? Because now your value isn't being rounded down anymore. Okay. So this is non-decreasing and it's converging to f of x star. And that's happening for all x star in AB. So we're really thinking of this as like a pointwise convergence, but it's doing so monotonically. Further, each of these functions fn is bounded. That's easy to see. All the values of fn must be less than or equal to n. Okay. And then finally, if your function f is measurable, then each of these functions fn is measurable as well. Now, why is that the case? Well, if I want to show that f sub n is measurable, then I need to look at the set of all x such, say, that f sub n of x is less than r. Okay. Well, if I want to look at this set, what I really ought to do is I ought to take the set of all x such that f of x is less than r. And then I'm going to intersect that with the fact that my f sub n of x caps everything out at n. So I'm going to intersect that with 0 n. Okay. Now, notice that this set is measurable because f is measurable. So for any r, this is measurable because f is measurable. This is measurable because it's an interval. The intersection of measurable sets is measurable. So for every r, this set is measurable, and hence f sub n is a measurable function. So what we have here, right, is we've constructed this sequence of functions. It converges pointwise monotonically to f. Each of the fn's is bounded and measurable. Since they're bounded and measurable, I can take the Lebesgue integral of any one of those fn's. Okay. So this sort of hints at what I ought to do if I want to define the Lebesgue integral of f, even though f is unbounded. Why don't I just take the Lebesgue integral of f1, Lebesgue integral of f2, Lebesgue integral of f3, and look at what happens to that sequence of Lebesgue integrals? Because each of the fn's is Lebesgue integral. So that's precisely what I want to do. So again, this is not a theorem, but rather this is just how we're going to define the Lebesgue integral of an unbounded measurable function. So let f be a non-negative measurable function on AB, and let f sub n be the sequence of n truncations of f. Then we define the Lebesgue integral of f on AB as, okay, the Lebesgue integral of f over AB is equal to the limit as n goes to infinity of the Lebesgue integral of f sub n over AB. Now, it's worth noting that this limit could be infinite. If it is, then we just say that this integral is infinite, okay? And this brings us to a small sort of difference between Lebesgue integrability and Riemann integrability. We only say that a function is Lebesgue integrable if this integral exists and is finite. Okay. For Riemann integrability, there's no notion of the Riemann integral being equal to infinity, right? We would just say that, well, that limit diverges, right? So here we only say that a function f is Lebesgue integrable if you can calculate the Lebesgue integral. and that value is finite. Now, all of this works perfectly well for non-negative functions. The next natural question to ask is what happens if I have a function that is, say, either negative or sign changing? Well, a pretty easy adaptation of this is to define this function f plus of x. F plus of x is defined to be the maximum of f of x and 0. And this function f minus of x, which is defined to be the maximum of negative f of x and 0. Now, in defining these functions this way, essentially what you're doing is if you have a function f that, say, is sign changing, so let's say my function f looks like this, then my function, so in green here I have f, my function f plus will simply be the positive part of this, and then where my function has negative values, this will just be 0. So this blue function would then be f plus. Now, f minus, it's easy to think it's just the negative part. It's actually negative the negative part, because I have this negation here. So my function f minus would actually look like this, right? So this would be f minus. So that's why you then get this identity then that decomposing things in this way, f is equal to f plus minus f minus. Now, why define f minus in this strange way? Well, by defining it this way, this ensures that both f plus and f minus are always non-negative functions. So we can then do all of this for sign changing functions by just applying our rules to f plus and f minus, right? So we basically say that a sign changing measurable function is its Lebesgue integral is you just apply this to each piece, right? So you can take the sequence of intruncations of f plus, the sequence of intruncations of f minus. You can look and see what each of those converge to. They'll converge to f plus and f minus, and then f will be the difference of those, right? So it gives us a way of sort of only writing down a definition for non-negative functions, but then we can actually apply it to sign-changing functions as well. Now, once we know, we've really said all we are going to say just about the Lebesgue integral itself. We've now defined the Lebesgue integral of both bounded and unbounded functions. There is another sort of subset of analysis called functional analysis, where you can go on to study different function spaces. So just from what we've done so far, you can start to see that you could define a set of functions, say L of AB, and I'm going to define this to be the set of all functions f such that the Lebesgue integral of the absolute value of f is finite. So these are really just the Lebesgue integrable functions, right? Because Lebesgue integrable means the integral is finite. And I can start to ask all sorts of questions about this set of functions. Now, it actually turns out that the structure on this set of functions is maybe not as rich as you would like it to be. But if you actually look at a related set of functions, so L2, we call this L2 of AB, and you'll see in a second where the 2 comes from. This is the set of all functions f such that the square of f is Lebesgue integrable. Okay. Now, it turns out that this has a really rich mathematical structure. In particular, you can this is an inner product space, so you can sort of do all sorts of things that sort of feel probably like things you did in grad linear, right? So you can define the inner product of two functions. In L2, the standard inner product is the Lebesgue integral over AB of f times g. Now, immediately, the question that comes up is, how do I know that this integral is even a finite value? Because if it's going to be an inner product, this needs to be a finite value. How do I know that this is a finite value? So you actually have to do some analysis then to prove that if the squares of f and g are both Lebesgue integrable, then the product of f and g is also Lebesgue integrable. But you can do that. This defines an inner product. Obviously, from any inner product, that induces a norm. So the norm induced by that inner product is just the integral of f squared to the 1/2. Okay, that's the norm induced by that inner product. Of course, now you can start talking about all sorts of topological or even geometric objects. Like you can talk about the unit ball, right? So you can define the unit ball in L2, say centered at the 0 function, right, of radius r, right? And that's just the set of all functions f such that the distance, well, I have a norm, so a norm induces a metric, right? So the distance between the 0 function and these other functions is less than or equal to 1. So this is a set of all functions f, so that the integral from a to b of f squared, this is d mu, to the 1/2 is less than or equal to 1. So that's like the closed ball, right? You can wonder, is this compact, right? Now that's a topological question. Okay, so we're not gonna go off and do a bunch of this functional analysis. What I want you to see is actually there's a very rich mathematical, a very rich depth of mathematical questions that come from defining this Lebesgue integral. And if you're interested in that, at some point, if we have the opportunity to offer an elective in our program, or if you go on and do more graduate work somewhere else, these are all questions you can answer after a course in some functional analysis. Now, the question you should then ask is, okay, if we're not going to do that, what are we going to do? Well, in the coming videos, we're going to return to one of the ideas we looked at towards the end of Math 5610, and that's of convergence of sequences of functions. Now that we have the Lebesgue measure, not even the integral, but just the measure, right, we can start to actually define other types of convergence. So we've already talked about we could have convergence of a sequence of functions point-wise almost everywhere, right? Similarly, we can have convergence that's uniform almost everywhere, but we're also going to develop other notions of convergence, something called convergence in measure, right? So we want to look at now that we know a little bit more about measure, what more could we say about convergence of sequences of functions? And then what that will naturally lead to are back to some of those same questions we asked in 5610, which is once I have a sequence of functions that's converging to some limit, what can I say about, say, the derivatives of the functions in that sequence? Do they converge to the derivative of the limit function? What about the integrals? Do the integrals of each of the elements of the sequence of functions converge to the integral of the limit function? Remember that the whole goal of Lebesgue integration was to really expand the utility of the Riemann integral to as large a class of functions as possible. So we might have some hope that it might play a little more nicely with those sorts of limiting operations. So what we will do in the coming videos are define those other notions of convergence and then look at how they interact with other limiting operations like differentiation and integration.